Good afternoon and welcome again to another one of our talks presentations. Today it's my great pleasure to introduce a friend, David Broman, who is on the faculty at Linköping University in Sweden, but he has been visiting University of California, Berkeley, and he will be here through the end of the academic year. David and I met a year ago and found out that we have lots of common interests in cyber-physical systems, model-based systems, back-end compiler construction, software engineering, and a whole variety of things. So I've invited David here both to give a talk, and I have a bit of an ulterior motive. I think that there are some potential collaborations here, that even though they may not get, the subject matter may not get covered in the talk, I hope you have an opportunity to stay afterwards and to engage with David and try to think about how we might be able to benefit from his expertise. And I think that this talk is actually going to be fascinating. So, David, I'm going to turn the floor over to you. Welcome.
Okay, thank you very much, Bob, for that kind introduction. So, before I start, I want to ask you all do you trust your processor that it always compute the right result? You don't have to answer. Do you trust your compiler that it always translate your source program correctly into your target language? So things are happening. And these kind of systems have a lot of computers, embedded systems. And these ones are, of course, developed and tested by human beings. And what we know is that people do make mistakes. And then, of course, what I said about correctness depends about what kind of system you have. And these kind of systems, the notion of correctness is a little bit different from if you take a web-based system or a standard desktop computer. So first I'm going to talk a little bit about cyber-physical systems and challenges that I see with cyber-physical systems. And then I'm going to go into one project that I'm coordinating called Modelyze, which is about modeling and analyzing systems, cyber-physical systems, and languages for doing that. And then I'm going to talk about what's called precision-timed infrastructure. That is a major project that we are trying to do to introduce notion of time in an infrastructure. Okay, so let's start with the cyber-physical challenges part. So, what is a cyber-physical system? You have ever heard this term many times. So it can be, of course, an industrial robot, a vehicle that we saw, a power plant, industrial automation, aircraft, and so forth. So the main thing is that you have a physical part, the plant, describing some mechanics or electrical parts, and you have some computers, typically embedded systems that are doing some computation. They can interact, so they can be any distributed systems. We have networks, we have sensors and actuators. So these kind of systems have been built for a long time, of course. So people wonder what's new about this. Well, these kind of systems become more and more complex and harder to design. And you want to develop something rapidly, so you can be the first one out on the market, but at the same time you want to have better guarantees of correctness, that they are actually working, instead of have very expensive testing, which is the case today. So what people are doing is to build models, to have abstractions of these kind of systems. We have physical systems and computer systems, and we want to abstract it. So we create models of these systems. We can create models of the cyber part, or the embedded part. For example, you can have state machines, you can have data flow formalisms, you can have discrete event formalisms, describing different aspects of the computational system. On the physical part, you also have models. So also the notion of the word model means very different things in different communities. So if you talk into a automatic control guy, a model, that is basically a set of differential equations describing the dynamics of the system. So you can describe that, and you can use modeling languages, such as Modelyze as one state-of-the-art language for doing this kind of modeling. And then if you have both these sides, hopefully you can do simulations to study the system, to do virtual prototyping, to study the behavior, dynamic behavior, before you even build it. Okay, so that is good. But if you want to have this kind of languages, you need to be able to have some properties on these languages. One thing that you want to have is expressiveness. You want to be able to express your modeling needs and also next generations. For example, in Modelica, you can see that you cannot express everything because in the current version, because every second year, typically there is a new release of the language, so that the language evolved because there are new modeling needs. And why is that? Well, these kind of systems are typically not Turing complete. So you cannot express everything. So you need to extend it. And even if they are, you cannot really express it in the right way of abstraction. It becomes a good modeling language. So it's easy to make something expressive if you just can do the computation, but describing differential equations by actually describing the solver is not a very good abstraction. The other part, if you want to be able to analyze, is to make some sense of the models, you need to restrict the models. So other part, you want to be able to analyze the model, to prove or test some properties. You can test it by doing simulations, for example. But you can also prove, perhaps if you have a restricted formulas, you can use, for example, model checking. But you can then not have too expressive models. There's a trade-off here between expressiveness and analyzability. So that, I would say, to be able to, if you look at the challenge of how designing modeling language, this is the trade-off and finding good ways of this is one of the great challenges when it comes to modeling languages in the cyber-physical domain. And I don't believe there is one solution that fits everything here. So this kind of challenges is something that we are addressing in this work, Modelyze. So I'll talk more about that. That is actually more modeling and programming language research direction. Okay, so we have models of the reality. And they are good. I mean, you simulate and you get some really nice result, maybe. Then the question, are these models useful if you cannot build this system, if you cannot realize this system? I mean, you're making this model because you want to study something, and then you want to create something that you can actually build. So if you take in general, we call it the model fidelity problem. That is to ensure that the actual model, if you simulate that, we're talking about the dynamic behavior of these systems, and the real systems actually coincide. So of course it's model, so you're abstracting away something, but that part of abstraction that you can simulate, you want to coincide so that the trajectory of the physical system coincide. And that includes both the hardware and the physical components. If you go in the other direction, going from model and doing refinement into the system, basically on the physical side, you have to create physical prototypes. On the other side, from the cyber part, the traditional way is that you have your models maybe in MATLAB, but then someone needs to optimize it and write a very good C implementation to make this work on a parallel machine. Then you kind of re-engineering the whole thing. You use the models to study the behavior, but then you reinvent the thing and implement it. So the goal here is instead to try to use these models and to compile or synthesize. Depending on whether you call it synthesize or compiling, depends on how much information that are actually not there, I would say. But there are similarities between them. You want to compile and synthesize down so you can use the models directly. The state machines, the data flow behavior, and so forth. So you get a more correct by construction. You have created a model and studied it, and then you go directly down to the system. So the other challenge that I want to emphasize here is this synthesis problem. To simulate, so that the simulated system that you can simulate and the real system actually coincide to a certain degree. Because we're talking about physical systems, there are always uncertainties, of course. But there's something here that is different if we compare to a compilation or synthesis problem in a normal system that is not a cyber-physical system. If you say a normal compiler in your desktop, what would you say is the main difference here? And that's also, I would say, the challenge, the main challenge. An idea what is different with this kind of system. Say, the notion of time. So the notion of time here is a correctness criteria. We have times describing in the model, part of differential equations. We need to have timing perspectives in the cyber part in the models. So we need to describe what we mean, even if we have a synchronous model of computation, like using Lustre or SCADE, we need to translate it into real time. And then we need to guarantee that this timing behavior actually runs exactly or close to that in reality. And this is what the second part is more about. Okay, so Modelyze. What is that? Well, it stands for model and analyze. And the main thing is that is a research language. And the idea is to address this, what I talked about, expressiveness versus analyzability, is to have a language that is extensible in itself. So you can extend properties within the language itself. So you don't rewrite a new language. Instead, you extend the properties within the language. And what we're doing is that we have this is a host language. So it's actually not really a modeling language, but it's a host language where you describe the semantics of the modeling language as a domain-specific language, which DSLs and embedding DSLs is kind of popular, especially in Scala community and in the Haskell community. And in that way, you describe different kinds of modular computation within this framework. And the main aspect here is that both the semantics, syntax and the semantics of the DSL and the actual model themselves are described in the host language. So you describe the models also in the language. Under the hood, this language is as a gradually typed functional language. Gradual typing means that you can mix static and dynamic typing within the same framework. It's called by value semantics. And the novelty for doing this, we're mostly focused on equation-based languages. So I'll show some examples on modeling physical systems using differential equations. We also looked into embedding a synchronous language, so a subset of Lustre. But the novelty is this typed symbolic expression that I will talk about later. We have a formal semantics of the core and proven type safety, for example, of this language. And there is also a prototype implementation that is you can download on the web. So there is a lot of related work in this area, especially in embedded DSLs and implementing DSLs. You can take very different approaches to develop DSLs. So we are following the more embedded DSLs where you're using the same language, the host language, and then embedding it so you get a feeling that you have a new language. I also have a lot of work on this combined static dynamic systems, static dynamic typing. We are using this to be able to have a trade-off between getting good error messages and being able to be expressive enough so you can traverse and do transformation of the models. And since this, what it actually boils down to is that this is a kind of meta-programming. So you're programming on the data structure of the language itself. And then it goes into the area of how do you represent code and data, and how do you inspect that. So, to be a little bit more concrete, we'll have an example, which is a classical example if you're doing physical systems. It's a pendulum. It's actually more complicated than you think if you are modeling it in Cartesian coordinates, that we're going to do right now. So we have the pendulum. The differential equations here are basically expressing Newton's law, so just in x and y direction. And then, since we have x and y directions, we also must have a constraint that is constraining the length of the pendulum, so that the ball does not fly away. So it's always constrained of the length of the string. It's basically Pythagoras sats. And then to be able to simulate it, you need to have initial values, so it becomes an initial value problem. This is how you would write it if you just write it in like in standard textbook, math book. So if you're modeling this, you probably want to do something similar in your language. You do not want to start to think about how do I do Runge-Kutta method now to be able to solve this. So if you simulate, you get this kind of behavior, just oscillates. So this is the pendulum described in Modelyze. It's actually not described in Modelyze, it's described in a DSL where you can write differential algebraic equations in Modelyze. And a differential algebraic equation, I don't know how many of you are familiar with that term, but it's when you're adding algebraic constraints to ODEs, ordinary differential equations. And that is often what pops up when you're constructing physical systems in a more systematic way. Okay, so this is the code. So we are using a function here, pendulum, that is basically a function definition for expressing the model. You see that it's got a couple of parameters, like the m is the mass of the ball, length, and so forth. We have unknowns, so we have this.
So are you doing computer algebra in the system, or are you mapping it into a discrete math, Rogakato or something like
You can say you go do both. You actually do a symbolic manipulation, so transforming the DA basically to an ODE, and then you're using numerical solvers. So there you have the unknowns, x, y, and t. So you give them the type, but not the value, because they are unknowns. And here we have the differential equations. And if you look at them, they are pretty similar. You have the prime showing the second derivative. So it's declarative in the way. It's also the equations you can change the order and move around the variables and it gets the same behavior. So then the question is, of course, since we're talking about it's being extensible, what part are actually part of Modelyze and what is part of the DSL? So the only part that is part of Modelyze is the first thing, how you define a function, a model, and that you have these unknowns. So these unknowns are actually under the hood what we call typed symbols. So they are symbolic values but they are tagged with types. So when you instantiate this kind of model, when instantiate means doing a function application, these symbols are created under the hood. The only thing you can do with a symbol is to create them and compare them for equality. So you cannot, they will never be assigned a value. So this whole language is otherwise a functional language where you just have one single assignment. There is no imperative way of changing a variable. But they're tagged also with a type. And then you have, if you have symbolic terms, the type of these terms becomes symbols, and you write that like this. You can write with a square bracket and then a type. And then it's a symbolic type of tau t. So in this case, we have x here is a symbolic type of type real. And when this code snippet is executed, it will create new symbols and replace them basically in the equations. Actually, the equations here are also not described in Modelyze. So you define what an equation is. And these definitions are also using type symbols. So everything is based on these type symbols. That is basically how you have a constructor mechanism. If you're familiar with Haskell's way of having algebraic data types, it's got very much similarities to that. Okay, so if you look a little bit deeper into this equation here. So as I said here, they are bound once, and now x is bound to a symbolic value. So if that value is a symbol, and then you do the power 2 on a symbol, if you could actually execute that, it's undefined. What is the power of a symbol? So instead, what is happening, what we want to do is to say that, okay, this is a symbol, we're doing power of it, so we want to lift this whole expressions into a symbolic expression, so it becomes a data structure. And then we want to lift all the expressions that cannot be evaluated into symbolic expressions. But the things that can be evaluated should not be lifted. So in this way, this whole system will be evaluated where it can, but where it cannot, it will be symbolic expressions. And these symbolic expressions will, in the end of this modeling, will be a set of equations, symbolic express equations. And that is when we're doing symbolic analysis and then solving it using a numerical solver. So what Modelyze is providing is making this much simpler than doing this. You don't have to write a new language. You just use these and then do these analysis afterwards. So one way of doing this, of course, to do this between code and data is to use quasi-code notation. How many of you have heard of that? Hands up. Few. So that comes from Lisp originally. So that is, you can explicitly say what is actually code and what is not. That is used in, for example, MetaML, which is a language for stage programming. And then you say, quoting, this is code, and then you can escape, say that, oh, this is not code, and then you can do this nested way. So if you would do that on this last line, and write it in MetaML notation, you would write like this. And of course, this is not very readable, and you kind of destroy the whole idea of making this DSL close to writing in math. I mean, it's really hard to write this kind of expression and get it right. So we want instead to do this automatically. And that is what is kind of the main contribution of in the Modelyze from a technical point of view, is this what we call symbolic lifting analysis. So what this symbolic lifting analysis is doing is that during type checking, it is lifting the terms that cannot be evaluated into symbolic expressions. So it's using the types to make this distinction. And compared to binding time analysis, partial evaluation, this is actually the reverse. So we are figuring out what cannot be evaluated at runtime. That becomes the symbolic expression. So this is a typing relationship. So normally there is no translation. It's just yes or no. Is this type checked or not? In the new translation here, we're also translating into a new term that will be the lifted term. So just to exemplify this, if we rewrite this into prefix query form, so you have prefix form instead of the infix form that you have there in the code snippet, and you have the division here will be a function taking two arguments. This is using the arrow syntax as in functional languages. You have this is a symbolic type, and L here is not a symbolic type. Under the hood, so this is something that the end user will not see. So now this is more describing what is happening under the hood. We're lifting this division symbol and encapsulating that into something that is lifted that then can later on be opened up. So you encapsulate the whole function. And then the applications, you see these symbols here, are symbolic applications. So it's basically turning the application into tuples. So this is how it translates into a data structure that can then later be inspected by another function. So this is the lift expression. And here we have the applications. So this is how it works, and then you create this, you get this data structure. So if we look at something, a very small function that is using such an expression. So if you take this pendulum and apply that to some values, the length and mass, it will returning a symbolic expression. And if you pass that as the input to this getUnknowns function, which will analyze this equation system and return a set of all other unknowns. So that is something that you, when you describe the semantics, the simulation semantics, you typically want to retrieve the set of all unknowns in this equation system. And then you have the equations, and then you transform this further. So here is where we're using this dynamic typing. So you see that we have explicit static typing. Otherwise, we give type signatures in the functions. But you can also, with this question mark, say that this is dynamically typed, meaning that it can be any type. And in that way, we can do traversal of the whole system here. So with these three rules, we can do a traversal of the whole equation system and find out all the unknowns. And by doing this with the dynamic typing here on the traversal, we do not have to have a big boilerplate code. So this is something, if you're looking at DSL development, which is a problematic, is that if you add more constructors to your data type, you need to change all your traversal functions. So this is making it more expressive when you're doing these transformations. And here we're basically matching for a symbol with type real, and we're adding it to the set here. This is just a symbolic application, and we're doing a recursion here on itself, recursively going down. And if we are in the end here, we return this accumulated set. The other problem that we're addressing here is about getting good error messages. So a problem in embedding DSLs is that typically you can get very nasty error messages from the host language. You can use, if you're used, for example, C++ templates and try to do embedding, you can get really messages that it's impossible to understand. So here we're using the type system also to getting fairly good error messages. So in this example here, we do not have any value. We've forgotten to write out the actual value for the initial value. So this init here is it's a construct that is described in the DSL, not in the host language. So the parser will accept this. But then if you do not do any check statically here, at the type segment, you will probably get an error message in the numerical solver saying that you do not have enough information, so you get a numerical error. And that would be very hard if you have, say, 20,000 equations, and you just, oh, I cannot initialize this. It doesn't help you very much. So you want to pinpoint the error better. And in this way, here we have the type system that you see, that you will notice that you have actually called this with one argument too little. And then you get this kind of message. The tricky thing is to make this work in embedded DSL. If you were designing your own language from scratch, of course, this is trivial. But the challenge is to make it easy to express these new languages and still get reasonable error messages. So just to get a little bit bigger example here, so we have a model mechatronic system, which has a controller part, a PID controller, some electrical components, direct current motor, and a mechanical system where you have a gear and then you have a shaft that is kind of wobbling, so you have many pieces together, so you have a flexible shaft. So you see that each of these parts down to the right here has a spring and a damper and an inertia that becomes why it becomes flexible. So the Modelized code for this would look like something like this. So this is another DSL where you can express a-causal modeling. So this is very similar to Modelica. So you basically can do basic Modelica simulation. So this is good for doing the physical model. This is not really on the cyber part. So here you see that the different components here are connected together using symbols. And these symbols are also described using type symbols. So the underlying mechanism is the same here, but now we're using it to connect different components together. And also the types here, you can see that you have a signal component or rotational component. You'll see you have electrical components. And since you have given different types on these different nodes, you will also have static error messages that if you're connecting a mechanical port to an electrical port, you'll get a type error. It says that you cannot do this, which is much better than that you get some strange simulation behavior, because that was not intended when someone defined the region libraries. So this is how the different components are connected together, basically using function application. You can also see here that you can utilize functional programming. So here you have a combinator called serialize, which takes as input a higher order model, which is a shift element, that it will then combine together again. And they say how many times will we serialize this 5 times. If we go down into the direct current motor, then that can have separate components. So you see you have a voltage, a resistor, and so forth. So you can have a hierarchies of models. But in the end, these are just function composition for describing this. And then when you go down to the lowest level, you have, for example, here the inductor. And then you have the actual equations describing the behavior of this inductor. And here you see the prime here, so the current is first derivative that is describing the behavior of the inductor. So that was my talk about the Modelized project, which is basically a way to encode different kind of models of computations. We have one of our students in Berkeley did has a small class project to embed this Lustre, a subset of Lustre for synchronous programming in this, and managed to do this in 3 weeks, I think. So the whole idea is to make it easy to do this kind of developing a new language from scratch in 3 weeks is not really possible. But so you have these models and you want to transform them into, on the cyber part, you want to do the correct construction so that you can actually transform the models into something that you can execute. And then we need a notion of time. So the traditional approach when we are programming something, so we have some sort of programming model, and then when we compile this into a target system, we get the timing the behavior depending on the platform. So we don't know this, what is the real timing behavior, because the actual semantics of timing is not really described in usual languages that are used. So if you talk about C, C++, you don't talk about real time. You maybe talk about some ticks that you invented yourself, but the semantic itself doesn't say anything about time or real time. So what the main objective of what we're trying to do here is to change this, to have time as part of the programming model. When we talk about real time, so you can express how many milliseconds or nanoseconds something should take. And if it does not meet these deadlines, what should it do in that case? Or do a different kind of enforcement. And of course, one consequence, if you can do this, is to get portability. So if you compile it for a new platform and the compiler verifies that it fulfills the constraints, it should behave up to some precision in the same way. Because today it's not obvious. You can take an old platform and you have your system and then try to put it to a much faster platform. And you can actually miss deadlines instead of getting a deadline. It's not, you cannot ensure that just because you think it's faster that it will be superior. So what is PRET? How many of you have heard of PRET? Hands up. One. Good, Bob. So PRET stands for precision time. And it was actually introduced, the idea was coined by Stephen Edwards at Columbia University and Edward Lee in 2007. And the idea is that we are doing the wrong thing. For this kind of systems, where the current architecture is not really well designed. Caches, for example, or traditional pipelines are very good for getting average case performance better and better. But that doesn't help if you're interested in the worst case. So instead, we need to change this, the architecture and all the stacks above. And now we're talking about not just PRET machines that we talked about from the beginning, but an infrastructure. That means that we have the hardware. We want to have computers that are more predictable, or processors that are more predictable, but also compilers that are timing aware. So they use the knowledge from a higher level language where you specify timing, and to make this as one infrastructure. So when we're talking about semantics, behavior of this kind of system, one thing that is always important in real-time systems, they interact with real-time, is about deadlines. You do some computation and you want to meet some deadline. And depending on what the consequence is if you miss this deadline, depends on which kind of applications you're actually developing. So traditional categorization is here to have hard tasks, that if you miss a deadline, it will be some catastrophic consequence. For example, a tight loop of the controller in an airplane. You do not want deadlines in that controller loop to fail. You have firm tasks where you typically you compute something and then you miss the deadline. Then nothing will be really damaged, but the result will be useless. So you cannot use it even if you finish the computation. So then you will just want to stop when you miss the deadline and start to compute something new. If you are, for example, streaming data in real time, that could be the consequence in sound or video. And then you have soft tasks where even if you miss the task, the deadline, you still have some utility, even if the utility might go down when you miss the deadline. It could be, for example, systems that are more interacting with human beings. So, and often a system could be a mixture of these different kind of deadlines. So if you're looking at the soft tasks, what you're interested in is to detect, if you want to have this kind of semantic, you want to detect, have a late miss detection. You want to, after you have actually executed a task, you want to detect, okay, I missed it, and maybe perhaps how much you missed it could be used for further computation. But late miss detection is not really useful for firm tasks. Because if you're already late, you've already done a lot of computation that was not necessary. So then you want to have a kind of immediate miss detection, that you detect directly when you miss it, you want to do something. So the semantics that we are, or construction that we are working on here, this immediately is more an exception based. You have an exception, timing exception. And of course, if you have immediate and late, you ask that what is the third thing? perhaps early misdetection, whatever that means. You detect something early. So in this case, you want to detect that you're going to miss something before you actually execute it. And that sounds pretty hard, because that is about predicting something. So we have a predictability here. We want to predict that will we miss this deadline? And to be able to do that, we have to explore all possible machine states and all possible inputs. And then typically what you do is you compute the worst case execution time to try to figure that out and use that to predict if you're going to miss this deadline. So predictability, one property that you want of this kind of infrastructure. Repeatability is another thing that you want to get the same behavior every time you run it. And you can look at it from on a platform-based point of view, just one platform. It's about testability. When you're testing something, and you're testing it again with the same input, if it's got totally different behavior every time, it's pretty hard to know if the test fails or not. Normal functional way of programs, we are kind of used to that. If you run the program two times, you expect it gets the same behavior if you don't have some weird concurrency going on with interleaving and so forth. But the other part is about portability. If you have many platforms and want to change, predictability is about giving the same behavior even if you switch platform. And the third property is, of course, the precision of timing. Because if you're talking about getting something with a precision at milliseconds, it's not that hard to do today. But if you want to go down to nanosecond levels, you need a different kind of precision, especially if you do not want to waste and to run this kind of system with very high clock frequency, because you maybe want to have a lower clock frequency and lower voltage and save energy. So this is a trade-off to find the right sweet spot. So all these parameters matters when you want to have an optimal system. So one part that we are working on here is the problem of this worst case execution time. So this is actually a research area of its own, the field. How do you find worst case execution time on a specific code segment, on a specific task? And if you just look at the worst case execution time here as a distribution, this is some made up distribution, some similar Gaussian distribution, you have some average case execution time, which in normal computing is what you aim for, that on average you want to be as fast as possible. But in this kind of system, if you have hard real-time problems, you're interested in the worst case. So just because it's good average case does not mean that it's good in worst case. So if this thing would look like this, but then slide out here very long, it would be maybe a very good average case execution time, but really, really bad worst case. And this is if you're thinking about cache. If you have a cache miss and cache hit. If you just assume that you always, in the worst case, have a cache miss, you will have very bad estimates on the worst case execution time. So a naive way of doing this gives a very big over, and then you will have a computer or an embedded system that is totally over. It has way too much power than you actually need. But to be able to guarantee it, you need it, because in the worst case, you can actually run into this phenomenon. So one way of doing this is to do a measurement-based approach. This is actually what is used in industry quite a lot, basically for the fact because it's fairly simple to do. So you measure, you run the system and do a lot of measurements. And the good thing is that you can do this, but you have no guarantees at all, because you're just taking some snapshots. And even if you can explore all the inputs, you need to explore all the machine states. That means all different configurations the pipeline can have, all different states that the cache can have, and be sure that then you can have measured all this, which is impractical in practice. So instead, you can do a more static analysis approach. You analyze the program, but you actually need to analyze the binary. So because you need to know in what way did the compiler compile down this code. And by doing that, you're probably not going to find the worst case execution time, but an upper bound that is safe. You want to have a safe upper bound. The problem is that we know that we can never find a method to do this for any program. An idea why that is the case, but why we can say that we cannot find this. Exactly. So if first thing we need to prove is termination. And if we can say that if program terminates, we have for any program we have solved the halting problem, which we are pretty sure that we cannot do. So the challenges here is to be safe, to always be safe, but then to be tight. So you want to be as tight as possible to the worst case, real worst case, and then to be scalable, that you can actually make bigger and bigger programs and analyzable. And I would say that especially the last part is the problem today, why it's not really adapted to industry. It's really hard to scale this up to real tasks. So what is our goal? Everything should be made as simple as possible, but not simpler. Who said that? Einstein. Or it's attributed to Einstein. I think people don't know if he actually said it. But. So I would say this: execution time should be as short as possible, but not shorter. Okay. What is this? What do I mean by that? Well, if we are executing a task and we have a deadline, there's no point of making it shorter as long as it meets the deadline. So if you're looking at one isolated task, you want instead to minimize the slack, but in that case you need to know about the worst case execution of the task. But instead you want to minimize other parts. For example, if you have control of the hardware, if you implement this on an FPGA, you maybe want to minimize the area of the FPGA. Or the memory, the size of the cache or scratch pad. Or you want to lower the clock frequencies, you get better, you can maybe lower the voltage and that then gain energy. Or if you have a mixed criticality system, you want to reuse these clock cycles to other non-critical tasks. There are many objectives here, but it's not just minimizing the worst case execution time. It's not just the only objective. But the challenge here is to be able to do this and still giving these guarantees. So fortunately, we have a lot of languages that do have the notion of time. We have all these modeling languages. So in industry, Simulink, Stateflow is used a lot, both on the cyber and the physical part. Modelyze is used especially on the physical parts. So it's kind of both these are also used together more and more in industry. Ptolemy is the work in Berkeley about doing heterogeneous modeling, for example, and Modelized is what I discussed here. There are many more modeling languages. But in common is that you have the notion of time, because when you're simulating this, you're also simulating what is happening dynamically over time. If you look at more low-level programming languages, where you actually, when you implement these kind of things, there are some attempts in history to do this with augmenting, for example, C with timing constructs. But they've never really taken off. And of course, you can ask yourself why that is the case. But if you do not have an infrastructure that they actually can enforce and be able to meet these languages, they are not really useful. In it, they might be good definitions from the beginning. At the lowest level, processes typically do not have a notion of time. Not real time that you reason about milliseconds or nanoseconds, but you can reason about clocks if they were predictable. So this is the major work that has been done in the group that I'm active now in UC Berkeley. This PTARM is a result of one of the students there. It's a precision timed ARM processor. So some of the key aspects here is that it's instead of using caches, enforces the use of scratch pads. And scratch pads are programmable memories. So that means that you're pushing the problem of doing allocation from the hardware to the user, or actually to the compiler. But the difference is that the compiler knows about what is going to happen. So that is another reason that it's not yet published, but we're working on way to do scratch pad allocations, where you take into consideration scratch pad allocation, where you have worst case execution time as one of the main objectives. Other thing is that gives predictability, and that you do not have good predictability in the normal processor is the pipeline. So you have branch predictors, which are harder to predict. So many people in the research community on worst case execution time try to do models of these branch predictors, and in this way get a safe upper bound on the worst case execution time. The approach we're taking here is different. It's basically you do a thread interleave pipeline, so you have many hardware threads and you interleave it. And by doing that, you do not get any data or control hazards if you have enough number of threads. And also it's augmented with a number of timing instructions to be able that you can do the reason about we have it in granularity of nanoseconds. So you can have get time, you can do delays, you can do exceptions as part of the ISA. You can think about it as a cache, but you decide what to load. So you're using DMA transfers. Right. Or the allocation schemes that are working now is actually dynamically, so you're inserting code, management code, and loading and unloading at the level of functions. And as a prototype, we have a VHDL implementation running on a FPGA Vertex 5. Right now, another student, Mike Zimmer, is working on the next generation here, which is more flexible, so you can have the dynamic number of hardware threads. I mean, you have an upper limit, then that you can say have different schedules. So you can say that one schedule is getting two threads are getting 1/4 each, and one is getting 1/2, and then they are interleaved in this manner. We also this is designed for more for mixed criticality systems. So you have some threads that are hard real time, others are soft real time, and that you can give cycles back from the hard real time to the soft real time. And a different, more technical thing is that we are targeting the RISC-V ISA. You know, if you have seen that, that is a new ISA developed in Patterson's group. It's called RISC-V because I think it's Berkeley's 5th RISC ISA. But the idea is to make a modern ISA that is simple enough to teach, but still good enough for doing serious research, and that is open. It has not got the restrictions that we have with ARM. And there is a number of related works here, especially Martin Schöbler has done work on trying to do this on the predictable Java processes. So, okay, so if we're looking at the hardware level there, assuming that we have something that is predictable, so that it's easier to reason about. And then we maybe do some inlining in inline assembly in a C program to be able to have use these instructions, say delays and so forth, that is part of this ISA. And then we compile into C. So C is quite commonly used as an intermediate language. To compile into C, code generates, and then you use this to compile to the platform. The thing is that if you do that, you're kind of losing a lot of useful information if you want to be able to predict something about the worst case execution time. Because then you need to figure out, for example, loop bounds or infeasible paths. And this information is much harder to analyze when you have the compiled binary. So instead, what we are currently working on is what we call PRET-IL, Precision Time Intermediate Language, where the idea is that you can compile either via C or directly to this intermediate language. And the difference with this intermediate language is that you expose timing constructs. So you have constructs for expressing timing, but you abstract away from the hardware details. So you do not say anything about what kind of memory hierarchy you're actually using. So it's a normal way of thinking in a compiler that you have intermediate language, you have different levels of abstraction. And the main difference here is that we're exposing timing at hard real time or real time at a higher level. And what we're doing right now is that we are not reinventing a totally new intermediate language or intermediate representation, but we're using LLVM's IR and extending it with timing instructions. But we are writing a new compiler backend from IR, from LLVM, down to this FlexPet machine. The reason for that is we want to have full control and also explore new optimizations that you can combine with worst case execution time, and which is not that easy to just go in and use LLVM's infrastructures today. It's also, as a side note, that code is written, our compiler is written in a camel functional language, which I personally think is much more productive when you're writing compilers, just to get the students to learn it as well. That's the problem. Okay, so that is our work on the compiler side. We haven't published that part yet, so I'm just talking about high level about that. The idea is, though, that this kind of intermediate language is not limited to this kind of architecture, but we're exploring it because it makes it easier. And I think that is the key to make this thing actually work, is that you must make the different layers easier to reason about. But nothing says that you can do a more traditional approach and do analysis of the cache and have the contract. And also, if you do not meet these deadlines, you can give feedback back about the worst case execution time. Because you can also have models where you're using this information to maybe change the schedule or do something differently at the higher level. Okay, so to conclude, so I first talked a little bit about Modelyze as a host language. So that we have mostly evaluated for doing equation-based DSLs. So it's used for the physical part of a cyber-physical system. For simulation, it's using embedded DSL approach, and we're using this symbol lifting analysis technique with symbolic type symbols to be able to get it easier and release this annotation burden that you otherwise get if you're using traditional techniques. We have these gradual typed symbols, and this enables the way to be able to transform and pattern match and inspect and then analyze these kind of models. The PRET intermediate language is the main thing that we're focusing on right now on this infrastructure. And we have also in the group worked on this hardware, where there's a lot of things that can be done there. So hopefully more groups are interested in working in this direction. We are probably going to release in the end of this year this FlexPret processor, and as open source as well. It makes it a little bit easier when the ISA itself is not protected. And of course, to make this work together, you need to have the compiler to actually be aware about time. So you can take a look at these papers if you're interested. That was all. Thank you for listening.
All right, we have some time for questions if you're willing.
Absolutely.
Okay, questions. And I have the microphone here, so.
And tested. And to what level?
One more time.
What verticals have you tested this? And to what level have you tested?
You're talking about the PRET infra.
The whole model.
Okay, so the first part on the Modelized part, we have tested it on doing this kind of modeling of the physical systems. So what we have tested there is, so I come from the Modelica background. So I've been working on that before. So we have tested it in mechatronic systems and also tried to do simulations and get these simulations per environment and see that they are equal. So to actually test it, validate it to a physical prototype, you have to build a physical prototype. So it tested with simulation between these systems. That is, we are also, that I didn't mention here, working on a new hybrid solution for ACOSA modeling, which is giving more expressiveness than you can today do with Modelica. So it's also, we are using this as a vehicle to start the other kind of model computations. On the PRET infrastructure part, that is based mostly on smaller benchmarks, and we have not tested it on a big system. So that is still challenging to actually do a big evaluation with a real system. So this is more studied as a theoretical and also benchmarking as well. There's a lot of things to be done on the application evaluation side, on the PRET side.
I was going to ask a similar question. You started with this wonderful picture of a car wrapped around a tree. And my question is, at what point do you feel like you can put your children in a vehicle that will not wrap itself around a tree as a result of having reliable, predictable, real-time control systems. How far are we away from that level of assuredness? And what are the key things to get us there?
I mean, things are happening all the time. As you know, the train accident in Spain, that I'm not sure, it's still counted as it was a human mistake, I guess. But the warning system was not in place. So it's always an interaction with humans and computers. I think the main thing to go this more correct by construction is to be able to guarantee at least what we have right now. I mean, it's not that bad. We are, if you think how many times you take the train or airplane and it does not crash, it's not that bad. But the thing is to be able to develop more advanced system at a shorter time and still keep this. I think that is the challenge. So to be able to have this rapid development of the technology we have right now, if you compare to the revolution in when you're creating circuits, before you have automatic synthesis from VHDL or a high-level language to be able to replace and route. We were doing this manually, but it doesn't scale. So if that technology was not developed, we would probably not be able to produce this kind of processors or systems that we can do today. So it's about scaling up to more complex, but being confident that it's actually working.
And I know we have some folks from NASA in the audience who are sensitive to exactly that. Exactly that. Arno, did you have a question along those lines?
There are very effective solutions that exist to compute the worst-case execution time automatically. So I'm thinking of the WSET tool by Absinthe. So why would you not go that way? And is there any benefit of using your approach over those quite effective solutions?
So Absinthe tools, that is Rainer Wilhelm's work and then have been commercialized, is probably one of the really successful commercial applications. And they are doing exactly that. They are modeling the pipeline and modeling the cache. That is the main benefit. And then they also have analysis at a higher level, or you can work together with other tools. The problem is, of course, if the level of complexity of the processor. So they are still limited to a certain level how complex, for example, the cache mechanism is implemented. So that would be they do not really scale to bigger tasks or more complex processors.
So, for example, would you be able to apply this to the, let's say, the PowerPC 750, which is actually the one used at NASA for most space missions? There is a radiation-hardened version of the PowerPC 750. So do you think you'd be able to target that kind of architecture?
So the approach here is taking actually a different route. It's to make the architecture simpler. So it's not trying to do analysis on an existing processor. It's to go in the other route to construct a process that is simpler to analyze. So that is the difference.
So that's on the print side.
That is on Pratt hardware side.
But on the Modelyze, you in principle could analyze.
Okay, so the Modelyze is actually not coupled on which technology you're using for worst case execution. So the modeling side is as a higher abstraction. So that is the idea with the intermediate language. That is the meeting point where you specify the timing constraints. Then how you're actually solving that depends on the compiler. So that's why I showed the route if you go into a standard processor, which we are not right now working on. But then you can use, for example, Absinthe tool to resolve the worst case execution time and then do scheduling on top of that.
So when we are dealing with this mathematical modeling and physics-based modeling, one of the challenges that we have right now is that the system, given the time and space, evolves, and there's the changes in the structural dynamic of the system, and the operating condition changes and affects the models. So how do you see we overcome that challenge?
So you're talking about that the structure of the system is changing. So you have different nodes.
Exactly.
And then are you using Modelica or something similar to that?
Something similar
Right.
to that. And then when you want to verify, for example, the safety properties of the system, you have to exhaustively go through the models and have the whole system behavior. So
I think actually it's two parts here. One thing is to be able to simulate these structurally changing systems. And if you're modeling with the a-causal way as Modelica, underlying is a differential algebraic equation system. And the problem Modelica has right now, you can do limited mode switching. But the thing is, if the index of the DA, this is very technical, but if the index of the DA changes, you need to do new index reduction. And Modelica do not support that specification or any of the tools. So this is actually one of the models of computation we are working on. It's not connected to Modelyze, just that we are doing experiments in Modelyze. And that is that you're doing switching modes, you're also doing index reduction. But then the difficulty is to make this efficient. So that is if I understand your question right, with models, different modes changing of the physical system. The other part on the verification, I guess it's more about if you have some, then is it a hybrid system that you're verifying?
it could be cyber or hybrid systems because it's very difficult to model all the conditions and so it gets very time-consuming.
I mean, verifying a hybrid system is a very difficult problem in itself because you have the combination of the uncertainty of the correctness of the solver itself. So I haven't been working in that direction for verifying hybrid systems. And I mean there are many people that have been working on it. For example, Hensinger's done a lot of work on that.
Oh, yeah. Thank you. This is sort of more of a culture question, I guess. How do you plan to get the mechanical engineers to use your functional programming language, or your CS person to use your Modelica, or are you seeing in the future some super new language, super language, whatever you want to call it, that is so nice, so pleasant to use, that everyone from the theoretical mathematician to the mechanical engineer or the electrical engineer, everyone will use it, or will it still be some kind of hybrid or multi-language environment that somehow gets integrated by a very powerful theorem prover or model checker kind of under the hood? What are you thinking about that?
You're touching a very difficult thing. I mean, getting people to actually use your things, and for sure there is a cultural thing, and it's an educational aspect of this. So Modelica is used today by a number of I mean, it's a pretty large community, not compared to many people that are using Simulink, but a couple of thousand engineers that are using it full time. That model way is not that far from what I'm using in Modelyze, if you're looking at the DSL perspective. So there's a difference between developing a new DSL and to using this DSL. So one thing that I used when I had other engineers to use it, I changed actually syntax, because syntax matters if people should actually use it. But as a computer science, you do not like to reason about syntax because there is no scientific question about it. There's a lot of opinions. So that's why it turned to be a more C Scala syntax. Originally, it was more camel style. But the other thing on the compiler part, I think that is totally different. So the compiler part, that is for computer scientists to write a compiler. And yeah, there's no easy way here. But it's for sure to get engineers to work. It's basically most engineers would say, well, I wanted to work in MATLAB. So that doesn't resolve me from an academic scientific point of view. That is not always that easy to handle, that you do everything in MATLAB.
You actually sort of answered your own question there, but it would seem that looking at MATLAB and LabVIEW and things like that and seeing to what degree this could be embedded in it or be an attached module or something of that kind, because people tend to sketch fairly complex systems in those languages, or even SysML could be another system against which you attach it, model feeding into a simulation system.
Right. So I mean, I think this touches also to the question: how do you get academic research into the industry? And there are different ways of doing it. I do not believe that my purpose with doing this Modelyze is actually not to try to make this the new standard in industry, because I just know I will never succeed. But to show, if you can show properties that appeal to industry, maybe, so we have one project going on here, it's called iSci-Fi. It's between UTC, United Technologies, Berkeley, Caltech, and IBM. And there you have a very interesting mix, because UTC, they are customers by IBM. IBM are interested in developing new tools. And we are looking at the more semantic aspects, how you can build in these things correctly. So I think going via the big companies is the only way to get an impact in industry. It's not that your language will change. Very, very little my language research actually evolve into big languages. More
And
like
of course,
inspired.
Edwards Group has a strong connection to the NI lab, you guys who are right in Berkeley.
Yeah, I mean, they are attending every each weekly meeting, basically. So it's more that things, ideas pop into their products rather than that they take the whole academic platform and put it in.
Okay, so we have